Hey folks, thought I'd look at a couple of your homework problems before tomorrow's lab quiz. So we're going to look at three homework problems, 25, 54, and 57. 54 wasn't assigned, but yeah, hey, it looked cool, so I thought we'd do it anyways. And then I'm going to take a little bit of time at the end of this video to review some old rules of exponents, something that's going to be important as we move through our work with sequence and eventually infinite series and power series. So first off here, number 25, you're basically asked to determine if the sequence converged or diverged. So you need to compute the limit as n goes to infinity of 1 over n raised to the 1 over n power. And this reminds me of a problem we did back in Calc 1. It reminds me of what we had to do to show that the limit as x goes to infinity of 1 plus 1 over x, all raised to the x power, was equal to e. And because of that, I'm going to say let's turn this into the continuous variable case. And let's look at this limit. The limit as x goes to infinity, 1 over x raised to the 1 over x power. Now, if you remember what we did back in Calc 1 to determine the limit as x goes to infinity, 1 plus 1 over x raised to the x power was equal to e. The key to doing that problem is you have to start off by making an assumption. We're going to assume this limit exists. If anyone's wondering, well, why can't we just substitute the infinity in, blah, 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 you don't know what 0 to the 0 power is. 0 to the 0 is one of those indeterminate forms. And so we have to do a workaround on that indeterminate form. This is the workaround. Now you assume the limit exists. You have to call it something, so why not call it y? So assume this limit exists and call it y. And that gives you something that looks like this. Alright, now it's looking like a mess, but here was the key. This was the key to what you did in Calc 1, and it's the key going forward. It's just, we don't do it that often, but it just pops up often enough that we should remember it. Trick. You have a problem up here in the exponent. To get this problem out of the exponent, natural log is your friend. So why don't we take the natural log of both sides of the equation, and when you take the natural log of both sides, I'm going to have to pull the problem up here. Remember, because natural log is a continuous function on its domain, there's a property that says because it's a natural, or because it's a continuous function, you can rewrite that mess as the following. The verbiage you may have heard is because natural log is a continuous function, you can pass the limit process through the continuous function, which allows us to get something like this. Hey, now that I have a natural log in here, I can use one of those old properties of logarithms and move this 1 over x out front as a multiplier. That's just an old property of logarithms. And now we look at it and it's like, well, it looks like it's a different form. 1 over a really large number, x is going to infinity, 1 over a really large number, that's 0. You can't do the natural log of 0, but if you look at the graph of natural log, as you approach 0, and you can only approach from the right side of 0, natural log isn't even defined for negative numbers. As you approach 0 from the right, the graph is heading down to negative infinity. So now you have the form of like a 0 times negative infinity. So we've transformed the limit from a 0 to the 0 power to 0 times negative infinity. Still can't take it to the hospital. But if you rewrite it, if you rewrite this mess as the natural log of 1 over x, and that's what multiplying by 1 over x means. You can do this. You now have it in the form of a negative infinity over infinity. That's one of the indeterminate forms that is acceptable to go to the hospital. And when you go to the hospital, there's no limit statement on the left side, so you're not doing anything on the left side. It's over on the right side. You're going to the hospital. And, now we use the hospital rule. Get the derivative of natural log of 1 over x. So remember, the derivative of natural log is 1 over that junk. So it's 1 over 1 over x. Well, 1 over x is x, times the derivative of 1 over x. The derivative of 1 over x is negative 1 over x squared. And then the derivative of the denominator, that's very friendly, that's 1. So you have the natural log of y equals, if you clean this up, x times negative 1 over x squared. That gives you, negative 1 over x. You can do this limit now. The natural log of y is equal to 0. That tells us, we have a natural log equation, going back to exponential form. It tells us y equals e to the 0. E to the 0 is 1. So y is equal to 1. So we have determined that the limit of this continuous variable, thanks to our work here, we've determined that this limit is 1, right here. If the limit of the continuous variable is 1, that tells us that our sequence, which it agrees with the continuous variable for all positive integers, they're identical, it tells us that this limit, it too must also be 1. And that was everything in 25. I thought it was kind of cool because we got to review logarithmic differentiation. We haven't done that in a while. And hospital rule, properties of natural log. And that's it for 25. All right, I thought we'd look at number 54. It's kind of like one that I would do in class as an example because it's an even numbered one. And I think in that block of exercises, the author kind of gave in the directions, you might be using the squeeze theorem on these problems. And we are going to be using the squeeze theorem. Give you some insight on what I see that tells me it's a candidate for a squeeze theorem. Notice the word is candidate for a squeeze theorem. As n goes to infinity, when I see the trig function, sine or cosine, well, we know the behavior of sine and cosine. We know that it's got this wave type pattern. So I'm thinking, as I go to infinity, my sine or cosine is a wave that oscillates between 1 and negative 1. 1 and negative 1. So that, when I look at this, I see sine. The first thing that pops into my head is, well, the sine of 6n is always going to be trapped between negative 1 and 1. It doesn't matter what n I have in here. 1, 2, 3, 4, 5, 6. It doesn't matter. The sine of 6n is always between negative 1 and 1. Just basics of sine. Now I look at this compound inequality and I say, well, it's okay for me to come in and divide all three pieces by 5n. So that gives me a negative 1 over 5n, less than or equal to the sine of 6n over 5n, less than or equal to a 1 over 5n. Make a better looking 5. And now hopefully you're starting to see the squeeze theorem come out. You look at this limit. The limit is n goes to infinity, negative 1 over 5n. That limit is 0. Look at this limit. The limit is n goes to infinity of 1 over 5n. that limit is 0. So as n goes to infinity, this limit's 0. As n goes to infinity, this limit is 0. The only thing that we can conclude, thanks to the squeeze theorem, is what's trapped between these two must also have the same limit. So we conclude that that limit is also 0. And that's it for number 54. All right, folks, number 57, that was one of your homework problems. And, you know, for this one, I kind of see this could be another candidate for the squeeze theorem. And what's pointing that out to me is I see an inverse tangent in there. I mean, first, when I kind of look at this problem, I see as n goes to infinity, my denominator is going to be getting incredibly large. And I tend to think if I have a number divided by an incredibly large number, I should be getting close to 0. Well, how do I verify that? Well, I verify it by, I see that inverse tangent. And, that's the one graph that I said you really needed to know of the inverse trig functions. That the graph of inverse tangent, it has this type of shape. It has a horizontal asymptote at negative pi over 2 and a horizontal asymptote at pi over 2. That tells me an inequality. That tells me that inverse tangent is trapped between negative pi over 2 and pi over 2. Well, if inverse tangent's trapped between negative pi over 2 and pi over 2, to get a 2 here, all I have to do is multiply each piece here by 2. So I multiply by 2, and that gives me a negative pi less than 2 inverse tangent n less than pi. And you may notice the difference between 57 and the one I just did, 54. 54 on the squeeze theorem, I had less than or equal to's here, and that's because it involved a sine function, which I know can take on the value of negative 1 or 1. Here, these are strict inequalities because negative pi over 2 and pi over 2 are horizontal asymptotes. Inverse tangent will never take on those values. Minor point, but I thought it'd be worth pointing out. Well, next, this n cubed plus 4, I can divide each piece by an n cubed plus 4 to get negative pi over n cubed plus 4 is less than 2 inverse tangent of n divided by n cubed plus 4 is less than pi divided by n cubed plus 4. And hopefully you see now that our work is pretty much done. The limit as n goes to infinity of negative pi over n cubed plus 4, that limit is 0. The limit as n goes to infinity of pi over n cubed plus 4, that limit is 0. And then thanks to the squeeze theorem, we have what's trapped in the middle. 2 inverse tangent of n divided by n cubed plus 4. It too must have a limit of 0. Squeeze theorem. And that was it for number 57. Hey folks, thought we'd wrap this up with a brief look at some really old rules of exponents. Things that you saw, you would have first seen way back at the beginnings of algebra. So like a beginning algebra class. The first rule that you're all going to remember these. When the bases are the same and you're multiplying, you add exponents. Second one, when the bases are the same and you're dividing, you subtract exponents. And this is true, of course, when the base is not 0, to remind our confused Michiganders. And the third one that I thought we'd review is when you have a negative exponent, how you can rewrite that. And these are familiar rules. I know they're familiar rules to all of you. But just to make sure that you see how these rules they're going to manifest themselves in the rest of our work with sequences, series, and eventually power series. When you see x to the n plus 1, I want you to be able to see that as being x to the n times x. When you see x to the n plus 2, I want you to be able to recognize that as x to the n times x squared. So when you see this, x to the n plus 1 over x to the n, I want you to be able to see that that simplifies to simply x. And there are two ways you could go about seeing how that simplifies to x. You could see that this simplifies to x by using this rule. You'd have x to the n plus 1 minus n, which leaves you with x. Or you could see that it simplifies to just simply x by noting that the numerator is an x to the n times x. That's what we have right here. And then the x to the n would cancel with that x to the n, and that would just leave you with an x. So for that reason, if you have an x over x to the n, yeah, I'd like you to see that that simplifies to, now most of you are going to say x to the 1 minus n. That's using this rule of exponents. I also will need you to be able to see that this is the exact same thing as 1 over x to the n minus 1. And now you can get this 1 over x to the n minus 1 by, just look at this. You can move this x to the denominator. That would leave 1 in the numerator. And if you move it to the denominator, it would become x to the negative first. That's using this rule of exponents. So you can move it to the denominator, you have this, and then you can use this rule. You're in the denominator, the bases are the same, and you're multiplying, add the exponents. So that would give you 1 over x to the negative 1 plus n, which another way of writing negative 1 plus n is n minus 1. So you're going to start messing around with exponents and rules of exponents in a manner that you're going to be simplifying. You won't see that till after spring break, but I thought, hey, what the hell, let's go ahead and review it while we're here. So that's it. Quick look at 3 problems from the exercise set and a basic review of exponent rules. Thanks for watching.